I've been looking at the wrong clock. I'm starting 2 minutes late because this clock here said it was time to start. I'm sorry about that. I got to pay attention to the right clock. I did go through and do attendance. I may have missed people just because I didn't see them. I don't see Amanda. Is Amanda here? And I didn't see James. James? Okay. We will start with looking at a homework problem. Homework problem number 3 from the assignment that was due Monday night. Why did I choose it? Because it had the lowest score, 83% on the of the homework problems. So let's look at how you solve a problem like this. So we start off, I have a swimmer bounces straight up from a diving board and falls feet first into a pool. She starts with a velocity of 4.2 meters per second and her takeoff point is 1.6 meters above the pool. Now you notice those red numbers. Those numbers are different for different people, right? So like I can't do my solution and then Reagan can't say, well, I'm just going to put in that number because he just did it, because you have different numbers. So what's the first thing that I've told you to do with the problem? Draw a picture. So I'm going to start by drawing a reasonable facsimile of the problem. Here's my diving board, and I have on the diving board my swimmer, and my swimmer is going to go up. Okay, so I didn't give myself enough space to really do this right. Up and come back down. And I know my picture goes from head to where the feet are going to be. Let's just assume that this red, well, I'll draw the red all the way down. There we go. So their feet follow that arc. This is a very high jump, it turns out, in my picture. Yeah, it said, she's good. That's all we have to say about that. Now, I have my picture kind of roughed out. What do I need to add to the picture? The values I know as well as what I'm looking for. So I know that she starts 1.6 meters above the pool. So I'm going to have X initial is 1.6 meters. And she also starts with a velocity of 4.2 meters per second. So I'll put V initial equals 4.2 meters per second. And, of course, she's going to land at the pool, so she'll have X final, and I'm going to put a subscript final, is equal to 0. There's one more thing I know that wasn't given. What's that one last thing I know that wasn't given?
Acceleration due to gravity.
The acceleration due to gravity. I know that she has an acceleration that's pointing down, right? So the acceleration is going to be minus g, or if you prefer, minus 9.80 meters per second squared, because it's pointing downward and we're considering up positive. Now I look at my questions. How long are her feet in the air in seconds? So I'm looking for time here. As I said, the first step is to think about your concepts. Right now we only have one concept, kinematic equations. Hence, my concept is done by just the recognition I only have one concept. It's going to be a kinematic equations problem. Next, I have to determine which kinematic equation is appropriate. So for the first part, I'm looking for time, and I have the initial and final positions and the starting speed and the acceleration. Only one of our kinematic equations related all of those. The one that I said 90% of your problems are going to use. So my equation that I'm going to use is going to be the one that relates them, which is, and since I put a final there, I put final here. Now, since my x final is 0, I'm instantly going to say x final is 0 to make my equation simpler. Now, for part A, the physics is done. All that's left in part A is math. That's why you have your math requirements for this class, so you can solve a problem like this. This is the first time we've had one like this. It's a quadratic, so I have to use the quadratic. I can't remember if it's equation or formula. Every time I get equations and formulas confused. But I will use a quadratic and leave that off to solve this. So I always rearrange it personally. You don't have to do it like I do it. I rearrange this so I have time squared, which means I'm multiplying everything by 2 and dividing by a, plus 2 initial speed over a t, plus 2x0 over a equals 0. And so that gives me time must be equal to negative 2v0 over a plus or minus the square root 2v0 over a squared minus 4 times 2x0 over a all over 2. Now this would be correct for everybody regardless of your numbers because I put everything in with just the values that are the symbols. But now you would need to put in your actual values for V0 and X0. And of course for A, everybody's going to have minus 9.80 meters per second squared. And you'll get two answers. One will be a positive answer and one will be a negative answer. Which one makes sense? The positive one. So the positive one is going to be your correct answer. And then you might say, okay, how come I have two answers if only one is correct? The other one corresponds to if instead of jumping off the diving board, she had previously been fired up from below, the negative time is the time that she would have had her feet at the water level on the way up, if time is 0 when her feet are at the level of the board. So there is some meaning to it, but it's kind of a hypothetical. If this had happened in the past, that's where she would have been. Whereas the future one, that's the one that makes sense. So that's how I find my answer for part A, the time she's in the air. For part B, what is her highest point above the board in meters? Now, this one could be confusing because the highest point above the board, when I first looked at that, I just thought the highest point, which is above the board. But what they wanted, apparently, at least from Lindsay's work, was it you, Lindsay, that came in, or was it somebody else? Did you come in and talk about this question?
Oh, the next one.
Okay, well, no, somebody came into my office. It must not have been you then.
I did, yeah.
Okay, it was Bridget, yeah. Her work was impeccable. I know she did it right, but the answer she used was the one for the elevation and gave her wrong. So it had to have been looking for the height measured with respect to the board rather than with respect to the water. That is, the x at the top minus x initial is what they wanted there. So there can be some confusion there. If you had confusion on that, let me know. Right? I don't want people to lose points because of an understandable confusion. Now there's some, you should have known better confusions you can have. But let me know so I can correct scores. If you did it right, I can go and verify you did it right. And it was just, I thought they meant this. Okay, so going on then, for part B, I am looking for a height at the top. So I'm going to say looking for x, and I'll use a subscript of, I'll use 1 today. Looking for x of 1, which is at the top. So up here is my x of 1. Actually, I'm looking for the difference between x of 1 and x of 0. What else do I know is happening at the top?
Velocity 0.
The velocity is 0. So I'm looking for x1 minus x0, and I know that v1 equals 0. So now for part B, I have to look and say, okay, what variables do I know and what do I not know? What am I looking for? And for part B, I know the difference in velocity between the two locations. I'm looking for the distance in elevation between the two locations, and I know g, and I don't care about the time. Since I don't care about the time, that shoots me straight to, for part B, using the equation, and you can just rearrange it different ways depending on what you're looking for. That equation. This is what I'm looking for. The v at the top is 0. And so it turns out to be very simple. It's just minus your v that you start with squared divided by 2a. Remember, A is minus, so you're going to end up with a positive distance when you do that. And once again, it depends on what numbers you have, what answer you'll get. But this equation would be correct for anyone. Now it's just math. Put your numbers in. And then finally, part C. What is her velocity when her feet hit the water in meters per second? Assume the vertical component of the velocity. Okay, now I understand your question reading this. Assume the vertical component of the velocity is positive upwards. That means that if it's a downward velocity, you put a negative. If it's an upward velocity, you put a positive. Because positive is the upward direction. Basically, what that's saying is I should have with my picture, it wasn't specified until now, that positive is the upward direction. As we go on through today's lecture, we'll see that coming up again, becoming more important when we're doing two-dimensional, three-dimensional problems. So finally, for the last part here, what's her velocity when her feet hit the water in meters per second? Well, I have already calculated the time she's in the air. I know the height difference. I can solve this either using the time that I calculated in part A, or I can solve it just like I did part B. Either one would work. I would use the method like I used in part B because it doesn't require a previous calculation. I don't have to worry about did I round off somewhere. Now, a rule for rounding off, never round off except for when you're reporting your final answer. Keep them on your calculator and keep all the digits, and then when you have your final answer, just apply rounding off there. If you're going to continue on with the calculation, keep the full digits on your calculator and keep going. That way you don't introduce round-off error into future calculations. So the way I would do this would be x final minus x initial is equal to v final squared minus v initial squared all over 2a. Now I want to solve for the v final, and so I just rearrange this. Move the v initial squared across. And then I finally just square root everything. Notice you square root everything. You can't just make this, oh, it's v0 plus the square root of. You have to square root the whole thing. And of course, technically there's a plus or minus introduced when you do the square root. So we have two possible answers, a positive answer and a negative answer. And that's where we have to use logic. What direction is she traveling when her feet hit the water? She's going to be down. So that means we're going to use the negative answer because she was going down. Another thing to get from this that was in one of the reading quiz questions you might have had, how does the velocity compare when you're going up at an elevation to when you're going down at that same elevation? Like she left the diving board in this problem at 4.2 meters per second. How fast was she going when she got right back to the level of the diving board but was going down? Negative 4.2 meters per second. How do you know that? Well, one way is simply to look at this equation. We have the v squared is equal to v squared plus this thing. Well, if x final is equal to x initial, that's plus 0. And so the v final has to have the same magnitude as the v initial if you're at the same elevation. If you're above, you're going to be slower. If you're below, you're going to be faster. The same elevation is the same speed, just opposite direction. Any questions about that problem? So we're all good? All right. Then, this is a repeat that I asked before because we've had some slight changes in the composition of the class. How do you plan to pay for expert TA? Because I've got to get that taken care of today. I was going to do it earlier, and then I realized we've had some changes, and I should probably get the number again.
Quick question,
Yes.
You had mentioned before that we might be able to get a physical textbook for $50.
Yeah.
Is there any way that the bookstore could order that on my account?
I don't know if they'd be willing, but I will ask them.
It'd be great to have.
Right, because at least last year, they did this gratis. That is, they made no money on, they spent money but didn't make money. 33. I was checking to make sure my change to your clicker worked, Bridget, and it did. Anyone else? I have 4 people that I can't tell who they are, so I can't tell you who hasn't answered. Okay. Yeah, another person just answered. Do you have you have your own clicker, Edward? No. Oh, I was looking at Toussaint. I saw Toussaint holding the clicker. Hey, I can't see him because the window is open behind him and there's too much light coming. I've got something. Seriously. All right. So we actually have the same number. We have 12 and 8. Edward, are you going to pay for it online, or do you want me to try to have the bookstore? Okay. Okay, so I will have the bookstore try to get 8 codes. It should go quickly because all they have to do is send us a document with the codes, right? It takes no time. So it should go quickly. Cross my fingers there. All right, going forward, I don't think it's a clicker question now, but I could be wrong. Now, typical motion is 3-dimensional. We live in 3 spatial dimensions. Those dimensions have to be identified as mutually perpendicular directions, and traditional definitions for the directions might be, well, we always have up and down as one of our traditional directions, and then we have to have 2 directions that are perpendicular to up and down, and they just have to be perpendicular to each other. So, for instance, I can put one arm out here and one arm out here. As long as those arms are perpendicular, that's a set of 3. I can go around like this. Anything is perfectly acceptable as long as my arms stay perpendicular as I go around the circle. So, we might say up and down, forward and backward, and right and left. Right and left is perpendicular to forward and backward, and both of those are perpendicular to up and down. Or we might say up and down, north and south, east and west. That would be another set of perpendicular directions. Goes up and down, it's common to both of them. And when I talk about forward, backward, left, and right, that's where it doesn't matter what direction I'm facing, they're still going to work. Whereas north, south, east, west, yeah, they do change as you move along the globe. Actually, up changes when you move along the globe as well, right? Because down is defined as the direction that the acceleration of gravity points. But at any location, that's perfectly fine. And now we should have a clicker question. Go forward. Nope, next. It's coming, believe me. 2-dimensional motion. 2-dimensional motion is when you're working with only 2 of our 3 spatial dimensions. So if you're driving around a flat town or a flat state like Nebraska. Nebraska does have very slight rises and drops, but it's fairly flat. So if you're driving around and it's flat, you can treat your motion as just 2-dimensional because you're not going up and down, you're only going north, south, or east, west, or some combination between north, south, east, and west. So if you're driving around on the roads of New York City, it's really only 2-dimensional motion. We will almost exclusively either work in 1 dimension or 2 dimensions. We've worked in 1 dimension up to now. Now we're going to start looking at 2 dimensions. And for this problem, there are 2 dimensions that are on the horizontal plane. Now if I wanted to choose my dimensions, since the streets are laid out perpendicular to each other, I would probably choose to have 1 dimension going. Okay, that color does not have good contrast with this picture. I would choose to have one direction something like, and the other direction something like, Now those don't look perpendicular on my picture, do they? But they are perpendicular. We have to recognize from perspective that those are actually perpendicular. It's just they don't look perpendicular because the picture itself is not a straight down overhead shot. So with those directions, then I have a car traveling, and I can define its position by saying how much it is along this direction. Take that off. How much it is along this direction and how much it is along this direction. I drew arrows. Those are the directions I'll consider positive. And we label them with something to say what direction they are. And traditional labels are X, Y, and Z. So I just choose this one to be X. So the X direction is going to roughly the right. And the Y direction is going, to the roughly up direction. And I can define any location, like I can define, okay, this car here is in the negative X direction because I had to go to the left, and in the negative Y direction because I had to go down. And so I can define it with components. I can say that car is, and what you're used to from graphs is something like what the X component is, let's say -1, let's make it 10, meters in the X direction, and -40 meters in the Y direction. Now that's getting hard to read, right? Can you even see what I wrote? I guess you can see it okay. So I can give the location in ordered pairs. You guys are, is everybody familiar with ordered pairs? Is there anyone who's not familiar with ordered pairs? Okay, good. So I can give it in ordered pairs. Now our textbook does not do this, but I'm going to, because it's the way every other textbook I've ever seen does, and it's the way we keep track of things. The normal way that we would describe this position, we could write it, like I said, as ordered pairs. But it is more traditional to say that this is -10 meters, and then I put an X with a hat above it, -40 meters, and a Y with a hat above it. I know, cray, whatever. In math, we just call them hats. What do those mean? The hat means a unit vector along whatever axis is indicated. So X hat is a unit vector along the x-axis. Y hat is a unit vector along the y-axis. But then that begs another question. What does it beg? What's not defined to most people in the statement unit vector along the x-axis? What's a unit vector? Well, a unit vector actually is exactly what the name means. Unit means one. Vector has direction and magnitude. So a unit vector, I'll combine these, is a vector with a magnitude of 1. Unity is another name for 1. So it's a vector with a magnitude of unity. What's the point of a unit vector then? It's to give us a pointer, to indicate direction without changing the value. So I take what I had written there, -10 meters, x hat. That means -10 meters times 1 in the x direction. So you put that together and it's -10 meters in the x direction. So when you see that -10 meters x hat, in your brain you say, okay, it's -10 meters in the x direction. -40 meters y hat means -40 meters in the y direction. And so we can specify the location using these vectors. And like I said, this notation, actually I don't think either of the notations I showed here are used in the textbook. The ordered pairs is not as common in physics as the unit vectors, which is prevalent. Like I said, the first textbook I've ever seen that didn't have them. So two-dimensional motion, where we're going to start off. Everything we're going to do today is going to be two-dimensional because what's the difference in two-dimensional and three-dimensional? Just one more level of complexity doing the same things. If you can do it in 2 dimensions, you should be able to do it in 3 dimensions. It's just more work. So a question just to make sure we've been paying attention. How many I put confirmed here because if you're into string theory or superstring theory, you'd come with different numbers, but those aren't confirmed. So how many confirmed spatial dimensions does our universe have? Superstring string theory is a combination of supersymmetry and string theory, if you care. Okay, give it another 5 seconds or so here. All right, we had Z, 0, 0. Z is Z. What am I saying? ZZ, 18, 1, and Z again. We had a vast preponderance of the class said we live in 3 spatial dimensions. Now, I said spatial dimensions because we believe we live in 4 dimensions. 3 are spatial. What's the last one? Person who put 4, what's the last one? Time. Time is the last of the dimensions, but it's not a spatial dimension, it's a temporal dimension. So 3 spatial dimensions, 1 temporal dimension. The time dimension doesn't have a direction to it like the others. All right, and what are the traditional definitions for the 3 spatial dimensions? By the way, am I the only one that's annoyed that spatial is spelled with a T rather than a C? I mean, we talk about space, it just seems right. Okay, any more? Moving on. We had 0, 12, 7, and 0. Now, I hate that color. The truth is, both of these are traditional. I use both of them as examples. I just want to make sure that we go back and remember that our traditional has up, down, and hey, we had up, down in both of them. And then 2 directions, and what, actually, it's another clicker question. I think it's not right after this, but I don't want to just ask the question and then have it right after. Okay, it's not. What's the relationship I have to have between the 2 non-vertical dimensions of my 3-dimensional space? They have to be perpendicular to each other. And since they're horizontal, they're also perpendicular to the first one. So all of our directions for our dimensions are mutually perpendicular. Each one is perpendicular to both of the other 2. Okay. This here is just a precursor to why we're learning this. Motion is independent in your perpendicular directions. So if I have something like my tennis ball, I'll not throw it to Reagan because I'll hit that. I'll throw it to Ann. If I throw this to Ann, as I throw it, when it leaves my hand, it's going up and toward her. Up the vertical direction, horizontal, I'll just say horizontal and vertical, toward her. What direction was the acceleration of gravity? Downward. So the acceleration of gravity is going to make the upward velocity component, we call it a component because it's a piece of the total velocity, it's going to make that upward velocity component change. It started going up, it's going to slow in the upward direction, come to a stop, and then come back down. Now, with our assumptions of physics that there's no air resistance, what was the acceleration in the direction from me to Ann? 0. So if there was 0 acceleration in that direction, what happened to the horizontal component of the velocity? It remained constant throughout the trip. And so I can solve this problem in 2 pieces. One is the vertical problem, one is the horizontal problem. What ties those 2 pieces together? Time. And so you solve the 2 problems basically separately, but you have time to tie them together. So the time that it took for it to rise from where I threw it up to its highest point and then drop down to Ann is the same as the time it took from it to go horizontally from me to Ann. And so that ties the two components together in your calculations. You gotta throw it back. My vision's so bad I don't even watch it. Really. It's coming. It's actually not that bad. I stopped playing City League softball in graduate school because I couldn't judge depths anymore. Made me sad. And I do wear my glasses sometimes when I drive at night, and always when I go to football games. Okay, so that's why we're learning about these components. Actually, not really relevant to what we're doing today, but relevant to what we've done in the past. Just some quick questions about what happens when you throw a ball up and it comes back down. This would apply just the same as to the problem with the diver. When I throw it up, what direction is the velocity right after it leaves my hand? Upward. So I'm going to have the velocity is pointing up here. What direction is the velocity at the top? Which is kind of a trick question. Okay, it's 0. The velocity at the top is equal to 0, so it doesn't have a direction. That's why it's kind of a trick. What direction is the velocity here just before it gets to the hand? Downward. So the velocity started upward, was 0 at the top, and then it came back down. Now instead of velocity, let's talk about acceleration. What was the acceleration here just after it left my hand? Okay? Did everybody hear the answer? Okay, let's have somebody else answer because she's answering every question perfectly. I want to make sure other people also have a chance to answer. What can you tell me about the direction of the acceleration just after it leaves the hand of the thrower? It's downward. And so it's going like that. And what's its value? 9.8. Okay, I'm just going to put minus g because it's quicker than putting 9.80 meters per second squared. I put the minus sign to indicate down. It's actually a little redundant. My arrow says down, and I have my sign saying down. Somebody who's even more anal than me might say, well, that means it's up because it's negative downward direction. And they would technically be right. What about when it's coming down? What can you tell me about the direction of the acceleration when it's coming down? It's still down. So over here I have acceleration equals minus g, still pointing down. What about at the tip top? What's the acceleration up there? Okay, I heard only correct answers, which is rare. A lot of times people say, well, at the top the acceleration is 0, and that's absolutely wrong. The acceleration throughout its motion was constant downward with a magnitude of g. When people say that the acceleration at the top was 0, what they're doing is confusing acceleration and velocity. Velocity is the rate of change of position with time. And at the peak, it stopped moving, right, for a moment. It was going up, it's going to start going down, and it's stationary for a moment. But the acceleration is how the velocity is changing. So if the velocity is 0 and the acceleration is 0, what's going to happen to the velocity in the future? Nothing. It's going to stay at 0. If the acceleration was 0 up there, it would just float. It would levitate at the top. It would be a completely different world. But we have a downward acceleration, so the velocity is going to change in the downward direction. When it's at the peak, you can be assured that a moment later, it will be coming back down because of the downward acceleration. Now, everybody I heard said this right. You might wonder, why does he belabor the point if everybody he heard said it right? Because there could be one or two people who didn't say anything and didn't understand. And I want to make sure everybody gets the information. I will relate something that happened yesterday in a different class. Or actually, not yesterday, Monday. I gave a quiz, I picked up the quiz, and I started going over the answers. And the first one, I said, now what's the answer? And one person said, oh, anyone who got this one wrong has real trouble. And I said, well, no, they just didn't understand the concept, because we don't want to be demeaning like that. And sure enough, the first one I graded missed that question. Some people will miss this point or that point. And to start saying, oh, you got trouble because you missed the point, that's not true. We're all in here to learn. If everyone knew all the answers, there wouldn't be any point in being here, right? There wouldn't be any point for any student to be here if they already knew all the answers. We're here to learn. So I want to make sure that I cover things for everybody so people who, were embarrassed to raise their hand when they didn't understand still have a chance. Now that is spending more time than I wanted on something. So, an example of two-dimensional motion. Here's a picture of just driving in New York City or whatever. You take a trip that has two pieces. You drive 9 blocks east and 5 blocks north. And you probably had something relevant to this on your reading quiz. What's the total distance traveled in this path? Okay, total of 14 blocks. 9 blocks plus 5 blocks is 14. What about the displacement? Yeah, I know from reading the book that it's 10.3. I haven't done the calculation, honestly, but I know it said 10.3 blocks for the answer. Now the question is, how do we get that answer? Because you need to know how to find it two ways. On the first exam, you will have to draw how to get this. You'll have to do it with a graphical analysis to show that you understand. So when we add vectors graphically, we use, my teacher in high school taught me tip to tail. Our textbook says head to tail addition. And what that means is I take my vectors, and at the head of the first vector, I place the tail of the second vector. So in this picture, the time sequence matches how we add vectors. We have the first vector here. Here's the head of the first vector. So at the head of the first vector, we place the tail of the second vector, and it goes up here. Now, the answer when we add or subtract vectors is called the resultant. Resultant is just the name for when you add or subtract vectors. And the resultant is going to be the line that starts at the beginning point and ends at the ending point. So I start the beginning point and I go to the ending point. And so that's the resultant that I have there. Now here I added it graphically. If you're going to add something graphically, you have to use a scale, right? Measure the length so they match your scale. You can't just say, this one, and I'm going to call it 9, and it's about this long, and this one I'm going to call it 5, and it's about this long. You need to actually use a ruler and make sure that you have a scale like, 1 centimeter equals 1 block, and then you measure it 9 centimeters one direction. Make sure you go perpendicular to that and do the 5 centimeters for the second one. Right? You can't just say, I draw some random distance this and call it 9. It has to be accurate. Do a scale. And then to determine the resultant, you just grab your ruler. You lay the ruler on here and the ruler should read, hey, 10.3 centimeters, and since my scale was 1 centimeter was 1 block, it must be 10.3 blocks. And for the angle, we specify the direction by measuring this angle. And so I get out my protractor. The words compass and protractor always get mangled together in my mind. It was even worse when I bought these new things, and they were both called, I think, protractors on the web pages. Only one can be a protractor. This one's the protractor, this one's the compass. So you use the, yes, this one's the protractor, this one's the compass. This says compass here. Right, so this is the protractor. So use the protractor to measure the angle. Now, to make sure, everybody probably has experience with the protractor, but just to make sure, actually I need to bring that up here and take a picture of it. When I was planning, I was like, oh yeah, I'll just take a picture of that. Let us just make a quick angle. I know you can't see anything yet. I know you can't see, but I will take a picture and then you'll be able to see. It's cool, huh? Actually, I'm going to put this on just to save us time instead of having to do two pictures. Okay, there I have a picture of using my little angle measuring device that we determined was a, I don't know why, it's one of those mental blocks. So I want to measure the angle. The first thing you have to note is that I put one of these lines along the baseline. I didn't put it on the bottom here where the numbers, or where the edge is. I put it along the baseline that's a solid line that goes all the way along. And then where the two lines meet is where the hole is, which on these is right at 3 inches. And then I can measure the angle. I'm measuring from here. I'm not going to use the one that says 180, right? Because that's not measuring 0 when they're right together. So I'm using the inner one here, and I just look to where that crosses. And of course, as you get older like me, you'll learn the camera's an awesome thing because things I can't normally read, I can read by zooming in. I actually use this connecting wires at home, trying to figure out what the voltage is on a little transformer. Take a picture, zoom in. So I look at this. This line is between 31 and 32. So I would read this as something like 31.9 degrees. I know most people, that was very redundant. You already knew how to do it. But it's important to make sure you know how to use the device if you're going to be required to use it on a test, right? Yes?
For the exams, do you want us to do it both graphically and analytically? Or
I will specify. If I don't specify, you have your choice. And if you have your choice, you should do it analytically. There was a list of reasons to do things analytically, and one of them is you have better accuracy. Right? When you're drawing the pictures, there's lots of errors like, did I draw that line at exactly the right angle? Did I go exactly the right length? When you're doing analytically, you don't have to worry about, did I do that part right? As long as you punch the numbers right in your calculator, it's good.
do we all have protractors in here?
Yes. Yes. One more thing. I made a measurement. I put units, but I'm missing something. What am I missing?
The direct.
Okay, I'm missing reference points, which I haven't got to yet, but is an important thing. When I get back to the picture, I will talk about those. But with measurements, there's another important thing you need. I need my uncertainty in the measurement. So I have to look at this and say, how much could I be off? Well, if you look at the width of that line, this side here is probably at halfway between the marks. And so, if my line is about, in fact, my 0.9 I'm sure is too big, honestly. Probably 31.8 would have been a better estimate. I would say my uncertainty is somewhere on the order of 0.3 degrees. So I have to think about, what's a cause for uncertainty? One cause is the thickness of the line. Another cause is, did I get the baseline on correctly? Another one is, did I have them crossing exactly at the center? All of those play into my uncertainty. And so if I were to measure this again, I might measure 30.6. Or excuse me, 31.6. 31.6 would be consistent with this measurement. If I had 30.5, well, that's below what this one gives for a reasonable measurement. I'd say, apparently my uncertainty was bigger than I thought. Okay, now going back to, not that, turning off the zoom. Going back to this picture, you measure the angle here. I don't remember what it turns out to be, and given we only have 5 minutes left, I'm not going to calculate it at this juncture. But I need to specify what my reference from is and what direction my angle is measured. So if I look at this, traditionally, we measure angles in a counterclockwise direction. And so I would take this direction. Here's my reference point. So that's east. Going counterclockwise would be going toward the north. And so I would say the angle, that Greek letter theta is what we usually use for angle, is equal to, what is it, 27.3 degrees. And then it's to the north of my reference line east. And that's the part you were saying. I need to have those references. Just an angle of 27.3 degrees could be 27.3 degrees in any direction from any location. But if I say it's 27.3 degrees north of east, it tells me that if I start from the east direction and then go north 27.3 degrees, that's the direction it's pointing. Any questions about the angles there? Yes? I just made the number up. So if it was 31.9, I'll just change to 31.9. I'm happy with that. Better? Yes, Diksha.
What did you say the reference line was?
The reference is where I'm measuring the angle from. So I chose to measure it from this horizontal line, and based on this here, my horizontal was east. And so I went from east toward north. Question, Michaela? No? Okay. I have a few quick slides here. A few quick slides that will come up in time. I swear, as God is my witness. There we go. Here's an example given in the textbook of adding vectors. Taking a trip from, I believe that's Molokai to Hawaii. You have these different pieces of your trip. First you go to Maui, and then you go out into the middle of the ocean, another place in the middle of the ocean, another place in the middle of the ocean. I'm not sure why your airplane is making all those stops in the ocean. But your end result is going from Molokai here to wherever that is on the island of Hawaii. You can take all those legs, you add them together, and you can add up the pieces and get the distance you traveled, or you can take the difference from starting to ending and have the displacement. And for that displacement, you would calculate just by adding up each one of those pieces of the vectors. And I gave you the example of when I was in graduate school, my teacher had a really convoluted, complex picture and had the students add it up, and they came back to the starting point. They were supposed to just write 0 and move on. But they were like, yeah, it was only like 2 students, but who spent the entire class period on that problem, just breaking each vector into components. This here is just reminding you to use the compass and the ruler. How do we break them into components? Apparently, yeah, it was 29.1. That's what the angle was. Apparently, I will teach you how to do this next time we get together, because it's time to stop.